Welcome to the next video in circle geometry. In this video I will discuss the relationship between the angle at the center and the angle at the circumference if they are subtended by the same arc. It turns out that the angle at the center is always twice as big as the angle at the circumference. So if the angle at the circumference is, say, alpha, then the angle at the center will be 2 alpha. And it doesn't matter where on the circumference the point P is, it'll always be double, as long as the point P is not on the minor arc, but we'll see an example of this later. Let's prove it to be true. Our aim is to show that angle AOB is twice as big as angle APB. I encourage you to construct a circle and draw in these angles and measure them with a protractor, just to see for yourself that this isn't some fancy mathematical trick. We know that AB is our arc with a center of O, and that P is any point not on the minor arc. So P is above the minor arc AB. I don't like saying above because the circle could be rotated 180 degrees and it would still be true, but it's good for this example. To prove this, we need to make a construction. That is, we're going to join point P with a center O, and we're going to continue it on to the point Q. This will create two triangles that we can use in our proof. Now we start our proof, and we do it by naming things that we know to be true. The first is that AO and OP are equal to each other. We have to give reasons for every new statement we make, and in this case it's because of equal radii. We can therefore say that triangle AOP is isosceles, and that angle OAP is equal to angle OPA, which we're going to call alpha. We can do this because base angles of an isosceles triangle are equal to each other. But we know that angle AOQ is going to be alpha plus alpha, because the exterior angle of a triangle is equal to the sum of the opposite two interior angles. This is a long reason, but worthwhile remembering as it comes up a few times in this course. We can therefore say that angle AOQ is 2 alpha, meaning that the angle OAP is half the angle to the angle OPA, and we have related it to half the angle at the circumference. So the other half of the angle at the center is going to be 2 beta. Now we'll bring together both halves as our proof and show the relationship between the center angle and the angle at the circumference. Angle APB is alpha plus beta. Angle AOB is 2 alpha plus 2 beta, which when factorized is 2 lots of alpha plus beta. But that's 2 lots of the angle at the circumference. So we have succeeded in our aim to prove that angle AOB is 2 lots of angle APB. We are now going to go through a straightforward example and a more involved one. Example 2 wants us to find the value of x giving reasons for our answer. I encourage you now to pause the video to see what reasons you can come up with for yourself. We have just learned that angle AOB is going to be equal to 2 lots of the angle APB at the circumference. So what we do is we halve the angle at the center, and that tells us that the angle APB is equal to 55 degrees. Pretty straightforward. I always like to answer the question that's been asked, and it's asked for what x is. It seems pretty obvious, but it doesn't hurt to answer the question as it's been given. Example 3 looks quite different to the straightforward use of the rule. Before beginning this example, I'd like to point out that in circle geometry there will usually be more than one way to prove something. As long as your thoughts are structured and your reasons are correct, you can go about proving what you need using any number of geometry facts. In this example, we're told that the line DOE is a diameter, and that OG is parallel to EF. Given that the angle DEF is 38 degrees, we're asked to find the angle OGF given reasons. Take note that the angle DOF at the center is on the same arc as the angle at the circumference, angle DEF. We are going to use the fact that the angle at the center is twice the angle at the circumference, but it's important that both those angles subtend the same arc DF. I encourage you to pause the video at this time and see if you can reason out the answer for yourself. Okay. To give you an idea of what I'm going to try and do, I'm going to firstly work out what angle GOF is. Then, because the triangle is isosceles, I'll be able to work out what angle OGF is. I start with angle DOG equaling 38 degrees, because corresponding angles are equal, and I've named the parallel lines in which they are equal. Now I'm using the fact that I just learned, that angle DOF is twice angle DEF, because the angle at the center is twice the angle at the circumference. So I double 38 and I get 76 degrees at the center. Therefore, angle OGF is 76 degrees minus 38 degrees, which gives me 38. Now I note that OG is equal to OF because of equal radii. This means that triangle OGF is isosceles. So angle OGF equals angle OFG, because base angles in an isosceles triangle are equal, and I can therefore say that angle OGF, which I'm trying to find the value of, is 180 minus 38, all divided by 2. And that's because the angle sum of a triangle is 180. Therefore, angle OGF is 71 degrees, answering the question. There are simpler ways of answering this question, but this was the path that illustrated the use of the circle geometry theorem we are investigating. In the next video in the series, we will look at the relationship of the radius and the tangent and their point of contact. Thanks for watching.